Okay, so now that we have defined an elliptic curve group, defined over a finite field and addition operation, now let us move on to the next operation, which is called point multiplication. So point addition we have learned, although the term is little bit used in a little bit incorrect way, in the sense that when we say point addition, that means p plus q, but when we say point multiplication, that does not mean p into q. Rather, it is actually a scalar multiplication, not a vector multiplication. That means we multiply some scalar d with p, which is nothing but d into p is equal to p plus p d times. So that we can perform using that definition only. So we have learned how to do 2p, and once 2p has been calculated as this point, then again we can add this 2p with p the same way, following the same definition, to calculate 3p and 4p and 5p in that way. Also, we have to remember that we have polynomial time algorithm. The algorithm we'll learn in the cryptography course, but remember that there exists a polynomial time algorithm to compute d into p with respect to modulo p. This is also important. If we would not have defined the elliptic curve on this modular arithmetic group, instead, if we define the elliptic curve over real numbers or rational numbers, then calculating d into p will not be an easy task, in the sense we will not have any polynomial time algorithm. Like analogous example I can give you in modular arithmetic, if you do exponentiation x to the power y, then we do not have any polynomial time algorithm to perform this thing. However, if we do x to the power y mod n, then we have polynomial time algorithm to perform. That means exponentiation is not polynomial time, not an easy algorithm. However, modular exponentiation, we have polynomial time algorithm, and thus easy task. Similarly, point multiplication for elliptic curve defined over real numbers or rational numbers, we don't have any polynomial time algorithm. But if the elliptic curve is defined over zp, then we have polynomial time algorithm to do this thing. This is very important because point multiplication will be required during encryption. Like in RSA system, encryption and decryption. Like in RSA system, we have seen that modular exponentiation is essential in your encryption and decryption both. So since encryption and decryption will be done by the legitimate parties, not by the attacker, so it should not be difficult, it should not be hard, it should be easy. Next thing is what is called a generator of a group that you don't know, but you don't need to know also. Suppose we take any element p, any point p, any random point p from that elliptic curve E defined over AP. Now, if we compute these operations one after another, p, 2p, 3p, we calculate in this way up to some point qp, you will be getting unique points. That may be q, may be 2, q may be 3, q may be 4, but up to some points you will get unique points, not repeating the previous values. However, suppose qp repeats any of the previous value. For example, qp is equal to same as 2p. So in that case, q plus 1p will be definitely 3p, q plus 2p will be 4p in that way. That means from that point it will repeat the cycle again. That means we will not get any more unique point of the elliptic curve. So how many points on the elliptic curve can be generated from p by repetitively applying the operator on p? How many unique points? That is q, and that is called the order of q, order of that element, order of p, order of that element on the elliptic curve. And this definitely p up to qp is a subset of points on the elliptic curve. Now this subset is called, it can be proved that this subset with respect to the plus operator also satisfies all the properties of a group. It can be proved that it satisfies all the properties of a group, and that's why it is called a subgroup. And this subgroup has been generated from P. That's why it is called that this subgroup is generated, the generator of this subgroup is P. This is the definition of generator. and order of P is equal to Q, meaning the size of the subgroup generated from the element P is equal to Q. Now we are interested in a P where Q, first condition is that Q should be very large, and second thing is that Q should be a prime number also. Remember that P and Q both should be prime number. So again I repeat, Q should be a prime number. Actually, in fact, if Q is not prime number, it can also be proved that if Q is not a prime number, then this cannot satisfy all the properties of a group. However, if it is a prime number, then it will satisfy the properties of a group. However, we require Q to be very large also. In that way, we just pick random elements P, and whenever we get a suitable value of Q, then we fix on that subgroup. So that means now, from now onwards, we will not deal with all the points in ZP even, all the points in the elliptic curve defined over ZP even. We are only focusing on a subset of those points on the elliptic curve, and which is generated from the generator point P. So if P is the generator point and D is a scalar, we have polynomial time algorithm to compute D into P with respect to modulo P. Now, what is elliptic curve discrete log problem? This is very important. What is elliptic curve ECDLP? Now, I think you have already got introduced to discrete log problem DLP with the TAs when they discussed the discrete log problem. So what is discrete log problem? There we have an abelian group ZP into multiplication. ZP is the set and multiplication is the operator, and G is the generator of that group. That means G square. Since now the operation is multiplication, so we will not do G plus G plus G. We have to do G into G into G into like that. So G square G cube. In that way, if up to G power Q you do, or G power P minus 1, since the order of the group is P minus 1, then we will generate all the elements of ZP. So that's why G is called the generator. Now if you pick a random element alpha from ZP, then it is easy to compute G power alpha mod P. As I said, this is modular exponentiation and it is easy. However, given this G, P and alpha, X, it is hard to compute back alpha. This is known as discrete log problem, because we don't have, till date, nobody has found any polynomial time algorithm to do this thing. Similar analogous problem exists in this field also, elliptic curve cryptography field also. As I have said that given this abelian group E defined over FP generated from P, if we are given D, then it is easy to compute D into P, which is equal to Q. However, given Q, P and this modulus P, it is difficult to compute back the multiplier scalar D. So this problem is known as elliptic curve discrete log problem, which is considered to be hard. Also, okay, and we are comparing the two versions of the Diffie-Hellman protocol. This is the Diffie-Hellman in modular arithmetic, which we'll also discuss in later in key management chapter of the network security. And this is the elliptic curve version of Diffie-Hellman. So this is very easy. A and B are communicating through insecure channel and they want to establish a shared secret key. How can they do this thing? So suppose they agree on some ZP and G. That's why those are called global parameters, ZP and G. G is the generator of the group. Now A chooses alpha from ZP randomly and B chooses beta randomly from ZP, and then A calculates G power alpha mod P and B calculates G power mod P, G power beta mod P, and they exchange these X and Y values with each other. And then what A does X to the power Y to the power alpha, and B does X to the power beta. And as you can see that both are in fact equal G power alpha beta. So this G power alpha beta can be used as the shared secret key K, which can be used for symmetric encryption in fact between A and B. However, the security of the scheme is that the attacker is, since these are communicated through insecure channels, so attacker has this G, P, X and Y all values in its hand. However, it can be proved that if discrete log problem is hard, then it can never calculate K, that is equal to G power alpha beta, without knowing either alpha or beta. Definitely if it can calculate either alpha or beta, then from x and y it can calculate g power alpha beta easily as a and b are doing. However, without knowing alpha and beta, alpha or beta, it cannot calculate g power alpha beta using any polynomial time algorithm. Till date nobody has invented such algorithm. So this is known as Diffie-Hellman problem or Diffie-Hellman key exchange protocol. Similarly, it has an elliptic curve version also. Here what we do, these are the global parameters, the elliptic curve and the generator point P. Now A chooses a random multiplier scalar alpha from the field Fp, B chooses a random multiplier beta from Zp, I mean Fp. Then X calculates alpha into P point multiplication, and this does beta into P and exchanges the value, and then it does what again received value is y into alpha, and it does x into beta, both of which should be alpha beta mod P, which is the shared secret key k between the two parties. Now the adversary is also getting the x, y and p, so it can be proved that if elliptic curve discrete log problem is hard, then adversary cannot calculate alpha beta p without knowing either alpha or beta. That is the elliptic curve Diffie-Hellman problem version. Now this Diffie-Hellman problem has two versions actually, computational Diffie-Hellman problem and decisional Diffie-Hellman problem. And similarly on elliptic curve also we can define elliptic curve computational Diffie-Hellman problem and elliptic curve decisional Diffie-Hellman problem. What we discussed just now is or are the computational versions, computational Diffie-Hellman and computational elliptic curve Diffie-Hellman. What about the decisional Diffie-Hellman problem? As we know that the difference between a computation problem and decision problem, which we have studied from computational theory. In computational theory, we have studied that a computational problem meaning some inputs are given and you have to compute some value, satisfying some properties or satisfying some constants. In decision problem, some values are given and you have to answer in binary 0 or 1, yes or no. So here, what is the decisional version of the Diffie-Hellman problem? For example, let us consider the modular arithmetic version. So in modular arithmetic version, computation version is saying that given g, g power alpha and g power beta, you have to calculate g power alpha beta. And decision version is saying that given g, g power alpha, g power beta, in addition to these three values, one another value is given which is called x. Now you don't have to calculate g power alpha beta, but you have to say whether this x value is correct or not. Now without calculating g power alpha beta, can we say that this x value is correct or not? The difficulty of this decisional problem depends on that. If we agree that without calculating g power alpha beta we cannot say whether this x is equal to g power alpha beta or not, then that implies that if DHP meaning decisional computational Diffie-Hellman CDH is hard, then DDH is also hard, decisional Diffie-Hellman is also hard. However, if we can compare the two values with certain guarantee, even probabilistic guarantee, without computing g power alpha beta, then we cannot conclude in that way. We cannot say that if CDH is hard, then DDH is hard. Now, what the cryptographic analyzers have shown that both of the problems CDH and DDH in modular arithmetic are hard. However, in elliptic curve cryptography, CDH is hard, but DDH may not be hard in some groups that we'll see later. That will not see even in your cryptography course, but that is part of advanced cryptography. Those will do in research in future may see this thing. So that's why basically almost all cryptographic protocols are designed based on computational Diffie-Hellman problem, not the decisional Diffie-Hellman problem. Now last that we'll study is elliptic curve encryption system, which is based on Elgamal encryption system. Elgamal has an RSA version also, not RSA version. Elgamal has this integer arithmetic version also, but this is elliptic curve version. And remember that this is a probabilistic encryption scheme. If you remember, when I was discussing RSA encryption system, I discussed in the last class deterministic and probabilistic encryption system RSA. The example that I discussed there is an example of a deterministic encryption scheme. But here you can see this is a probabilistic encryption scheme. How we are doing this thing. So it has three phases: key generation phase, encryption phase, and decryption phase, like in RSA. So in the key generation phase, we define an elliptic curve first, then we take the generator point. Now we choose a random random value d from this field, and then we calculate q is equal to d into p. Now this q serves as the public key, and d remains the private key of the party, some party. So d is the private key of the party and q is announced publicly with these parameters also. Only d remains secret. Now this is the encryption. So we take a message, and then how do we do the encryption? As you can see, the encryption algorithm, in addition to m and the public parameters, public key, it is also taking a random number r. So as I said, that any probabilistic encryption scheme actually takes some random source of randomness. So this random number is generated from this field. Then what do? We do a point multiplication r into p. P is the generator point. Then this part is says c1 is a point. And then what do? R into q. Q is the public key. Is another point. Now what do we do? M XOR that r dot q. This XOR, bitwise XOR operation. That means this is simple bitwise XOR operation between the two. We convert the points into string, binary string, and then do the XOR operation. So that means the message, now C1 and C2 both, the ciphertext is pair of C1 and C2. C1 C2 pair is the ciphertext. Now that is sent to the party. Now how the party will decrypt it and how adversary cannot decrypt it, that we'll discuss. Now how the intended party can decrypt it. Now the message is actually masked inside C2, masked using R into Q. So if we can retrieve R into Q, we can retrieve M. Now how we can retrieve R into Q? Let us see what is R into Q. R into Q is nothing but R into what is Q? Q is equal to D into P. Now we can say this is equal to D into R into P also, D into R into P also. Now you have seen R into P is C1. So that means this is equal to D into C1. So this side does actually the same thing. So it first does D into C1. So D into C1 definitely will give you this R into Q. So now since XOR operation, you know, X in XOR, if message is M and key is K, then M XOR K gives the ciphertext, and ciphertext XOR K again gives you back the message, because M XOR K XOR K, K and K will cut and M you will get. So this way you get the message back. Now the point that the adversary will not be able to retrieve the message, how can we place the arguments for this? If you look into here, that in order to retrieve the message correctly from the ciphertext, you need to know R dot Q. Otherwise there is no other way to get the correct value of M. This is called the mask. You have to know the mask. Now how can you get R dot Q? The adversary knows C1, that means R dot P. It knows Q, that is equal to D dot P. It needs to calculate R dot D dot P, because this is equal to R dot Q. Now this is exactly same as the elliptic curve Diffie-Hellman problem. Elliptic curve Diffie-Hellman problem, just now we have discussed that if you are given Diffie-Hellman protocol is here. Yeah, alpha p is given, beta p is given to the attacker needs to calculate alpha beta p, which is a hard problem. So here also it is written elliptic curve computational Diffie-Hellman problem version. So here we can see the attacker has RP in its hand because C1 is transmitted open, Q in its hand because that is the public key, D into P, but it needs to calculate R into D into P, which is definitely calculating. If it can calculate R into D into P, that means it can also break the hardness of elliptic curve Diffie-Hellman problem. Elliptic curve Diffie-Hellman problem is considered to be hard. So the security of elliptic curve encryption Elgamal system depends on the difficulty of computational Diffie-Hellman problem on elliptic curves. So this is an example of probabilistic encryption system. As you can see that if we give the same message different times, we'll get different ciphertext, because every time the random number will be different. So this is an example of probabilistic encryption schema also. We're not getting the same message again and again. But one thing I forgot to mention, that while discussing the RSA encryption system, I said to you that I'll also show how using hash function we can make the simple RSA encryption mechanism probabilistic also. So this is a slide explaining that thing. As you can see from here, this is the mechanism actually explaining how we can make RSA encryption probabilistic. So here you can see M is the message. What we are doing, RO is written here, that stands for random oracle. You can assume any hash function we can use in place of RO. I think you can see it clearly. RO is a hash function. So what we are doing, first this is encryption and this is decryption. This is decryption. So what we are doing, first we are taking a random number R, we are generating a random number R, and then from Zn star, and then we are in fact encrypting that random number with the public key R to the power E mod n. Instead of encrypting directly the message, we are encrypting that R to the power E, and that we call C1. Now we are taking the hash of that R, random oracle of R meaning hash of R, that gives a string, and then we do again the same thing, bitwise XOR the message with that Y, hash of the R. So this is C2. So the pair C1 C2 is the ciphertext which is sent to the recipient. Now definitely here the same thing also, that in order to retrieve M from C2 you need to know the mask Y. Now you cannot get Y unless you know completely what is R, because a random oracle gives a completely random string for every input. So even if you know the other outputs or millions of input output pairs, doesn't matter, you have to know exactly what is the value of R in order to get Y. Now how can you get R from C1? So that is RSA encryption problem. Given R to the power E mod n, you cannot get given C1, that means R to the power E mod n, you cannot get R without knowing D. That is RSA encryption security. But if you know D, then definitely you can just do power D, and then you can retrieve R, and from then you can retrieve back M. So based on RSA encryption security, we can design RSA a probabilistic encryption system in this way. So here also we can see that for same message different times different ciphertext we can generate. So this is also probabilistic version of the RSA encryption. Original RSA encryption was not probabilistic, but as we said that is not end CPS secure. So that is the end of this part. Thank you.